I have already done a few episodes about AMR or grid codes versus particle-based codes. But which one is better? Welcome to the fluid mechanics war! This is Euler versus Lagrange. So the topic of this video is highly controversial. Like, it feels like a Pepsi versus Coca-Cola thing in the field. Either you are like a grid guy or a particle guy. Obviously, if you ask some of the big faces in grid-based codes, they will say like, no, grid codes are better. But if you ask the same question to these guys here, the guys in the particle business, they will tell you these particles are better. I'm going to make a brief episode about this, even though I know it's going to cause me some serious trouble. So just to give you a background, I did my PC using particle-based codes, and then I'm changing into grid-based codes. Which one is better? Still don't know, but I'm going to mention a few advantages and a few deficits that each code has. For me, the main advantage of the particle-based code is that you don't need to have a geometry in advance. So you place, in your initial conditions, you place your particles as you want, and then it's just the physics laws. And if you are using SPH, then all the density computations, all the quantities calculations come for free. And I mentioned you before that I made a mistake, and I have these jets ejecting from my stellar particles. That is calculated automatically. The shape of my cloud, like here, this is an example of a cloud that is changing shape drastically. It doesn't require extra computation to calculate the geometry. Whereas if you're using a grid-based code, the grid has to follow the geometry. That causes some overhead on the calculations of the hydrodynamical forces. But what is the problem with the particles? Is that nothing prevents two particles to be on the same position in our code. Nothing. So we need to introduce this thing that is called artificial viscosity. It's basically an artificial force we introduce when two particles are just getting closer and closer and closer to prevent them to be on that position. What happens is sometimes in astrophysics and in other sciences, you are modeling gas, and the gas gets really hot. For instance, if you have a supernova, the supernova is going to expel a lot of very hot material at very high speeds, and that material is going to collide with the natal cloud, like here. And when it collides with the natal cloud, it shocks it and compresses it. So particle-based code, because we need to introduce this artificial viscosity, don't deal with these shocks as good as grid-based codes, where the physics in that part is better resolved. There's another thing about grid-based codes. When you combine them with particles, some grid-based codes like the one I'm using have like the gas and then the stellar particles, and the gas is computed in grid and the particles is computing like in a particle-based code. And that is a really cool approach, and it kind of let you have a little bit of the best of two worlds. But another advantage of grid-based codes is, for me, it's when injected feedback. So I used the example of the supernova before. So if I have a particle in SPH like this one and I want to inject feedback, I need to go around and look for the closest particles so that I can inject momentum and energy to them. But if I have a grid-based code, on the contrary, I just can inject that feedback to the adjacent cells, which I know where they are. Sometimes they are even stored in the same node, which is it's really cool and fast. So it's still undecided which one is better. And to make things more complicated, in the last few years, there has been some hybrid cores like a repo, which is a mixture between a particle-based code and a grid-based code. And here you can see some showcase of this code that is basically considering the grid as something that can change with time, like if it was particles, and you can see here how the grid moves and evolves, and I think it's pretty cool. However, my point of view is the overhead of calculating the grid here, how it changes on each time step, is bigger than any overhead you will have from the change of the grid which is more regular in AMR codes. So if you like this episode, please click like. If you want, you can follow me on Twitter, YouTube, and Facebook. And see you guys next week. Bye bye.